Yes, scholars, today we're going to continue on with Unit 6 notes. This is 6.2 wave behavior, so please get out your notebook and label it with today's date and 6.2 wave behavior. Make sure you have the notes from last class opened up as well, because the information you learned in 6.1 will be useful in understanding 6.2 as well. Here are a few equations that we'll be using in Unit 6. These are the wave equations. This first symbol right here is a lambda. Then we have an S and then a T, and we will look at what each of these variables mean. So take a minute, write those down in your notebook. S is wave speed, which is measured in meters per second, just like velocity. Then, like I said, that upside down Y is a lambda symbol representing wavelength, which is measured in meters. And I always remember that that's measured in meters because length, of course, we would think meters. Then T, capital T, is period measured in seconds. So I think of T as time. That's how I try and remember it. But make sure you notice that the S is lowercase and the T is capital, and then the F stands for frequency, and notice that that is a lowercase f, and that is measured in hertz. That can be also written as capital HZ. So we are going to look at using these equations. So the first problem we have is a water wave hits the shore every 15 seconds. So every 15 seconds, another wave hits. What is the frequency of this wave? Well, out of our three equations, we are going to choose F equals 1 over T. If you weren't quite sure what the period was, you could have looked at the units to help you out, and which of our, if we have the seconds, it's asking us for our frequency, so we know this number here, 15 seconds, is our period, so we're going to use the equation F equals 1 over T, so F equals 1 divided by 15 seconds. Notice I have my units. So our frequency of the wave is 0.0667 hertz. You should have gotten, so make sure you have that example in your notes. Example number 2, a slinky wave has a frequency of 0.4 hertz. What is the period? Well, we have our frequency. We're looking for our period, or our capital T, so we're going to use T equals 1 over F. Plug in our numbers with our units, 1 divided by 0.4 hertz, which gives us 2.5 S, or 2.5 seconds. Next, the speed of a crowd wave is 7 meters per second. If the wavelength of the crowd wave is 35 meters, what is the period of the wave? So right away I'm thinking, okay, I have S, I have my lambda, I'm looking for my capital T, which is period. So I'm going to use lambda equals S times T. Of course, I'm going to rearrange the equation just like our other physics equations. So I want to get T, capital T by itself to get period by itself. So using my algebra, T equals lambda over S. Plug in my numbers, 35 meters divided by 7 meters per second. Well, 35 divided by 7 is 5, and we're looking at our period, our T, which is then 5 seconds. We're next going to talk about how waves can interact with matter. Remember, matter is anything that has mass and takes up space. So we have a few different definitions that it is important that you write down. Our first definition is transmission. And these are words that I would make note cards with, maybe with a picture on the back in the definition. So transmission is the bending of a wave due to the wave traveling from one type of medium into another. So one material into another. Reflection, which you're probably the most familiar with, is the bouncing of a wave off of a surface. So you could see your reflection in the mirror. You see the waves bouncing off the surface. And then diffraction is the bending of a wave as it goes around a barrier or through a hole in a barrier. So this is an example of transmission. The pencil is just in the air as the first medium, and then it changes the medium by going through the water in the glass, and notice that it looks a little bit different. Next, we can see reflection. So this is just light reflecting off of a surface. It's bouncing. Next, we have diffraction. So this is going around a barrier over here. We could also see waves here going, it's going from left to right. It goes around the barrier or this wall. Here are other examples of transmission. This is why fishers sometimes have challenges, because when they first look at the water, the fish looks like it's in a different place than it actually is because of the transmission of the light waves changing when the fish is in the water versus the fisherman who's out of the water not seeing it clearly. And then we also see transmission here as well as reflection of the light bouncing. And then the transmission of the laser we see going from one medium to another medium. And then this is a very fancy graph talking about reflection. If you go on to take AP Physics, you will be able to analyze all of this, figure out all of the angles for why things are reflecting the way they are, but we will not go too far into this right now. So normally, in a normal reflection wave, we see the incident ray, and you won't need to know these definitions, but just for your information, something reflects down and then goes across. So like if you think of blacktop, you might see or a sidewalk, you might see a reflection sometimes, and that is kind of what is happening there. And then we can see the waves happening here as well. Next we have diffraction. This is just another diagram that shows the bending of the waves around a barrier. And then we can talk about what happens if two waves interact with each other. We have two different types of interferences. The first one is constructive interference, which is the combining of waves to produce larger waves. And this makes sense because it has the word constructive, which looks like construction, and a construction worker builds things. And constructive interference, things are building together, getting higher and higher. And then we have destructive interference, which is the opposite. Destructive interference is the combining of the waves to produce smaller ones. So you can think of the word destroying, or something is getting smaller. If it's destroyed, destructive interference, the waves are getting smaller. So here is an example of this is one wave with another wave, and they can construct together to get even bigger, greater amplitude, if you remember back to the other video. So these three waves these two waves construct together to get this. And notice they're going down, down. So if we add this portion to this portion, we have constructive interference. Versus this is destructive interference. We have waves going the opposite directions. So this is going down in amplitude, this is going up, and it is destructive, getting smaller overall. And then this is another example of destructive, but these waves are exactly the same, equal amplitudes. So thus, we are left with nothing. And then here are just some more examples of waves interacting with each other. Constructive, again, we said the combining, so we see here the construction, and then here's the destruction, or destructive interference. And you will look at more examples during your virtual asynchronous day. If you're not taking iStep, we'll look at even more examples of this, and you'll create your own. Next, we're going to talk about standing waves. Briefly, standing waves is the combining of the incoming and reflective waves so that the resultant appears to be standing still. So each of these have nodes and antinodes. Node is what is a capital N here, and it is the point where destructive interferences cause an amplitude of 0 on a standing wave. So notice here, there is no amplitude, and that is a node. That's how I remember it. No amplitude is a node versus amplitude is an antinode. It is the point where constructive interference causes a crest and a trough on a standing wave. And we talked about in 6.1 that a crest is the highest level of amplitude, so right here, versus a trough would be right here. Notice that there's always one more node than antinode, because here we have 1, 2 nodes, 1 antinode. Here we have 1, 2, 3 nodes versus 2 antinodes. Make sure you have those definitions written down. And here's another example of nodes and antinodes in a standing wave. make sure you jot down one of these pictures as well. And then, like I said, you will look at more examples of 6.2 during your virtual asynchronous day. Thank you for tuning in.